Hello everybody, my name is Guan. I'm a graduate student in Columbia University.
My name is Alexander Gazman. I'm also a graduate student at Columbia University.
Today we are going to present you the Class D amplifier design that we did in the VLSI design lab. Here I'm going to present the chip layout. As you can see from the screen, on the left hand side is the chip layout in cadence, and on the right hand side is the optical picture of the fabricated chip, and the signal flowing from the bottom up to the top. And here is the output driver, which occupies like half of the chip area, and the other components, which we are discussing later, are sitting here.
Now I'm going to present the PCB that we designed to test our Class D audio amplifier. The audio amplifier chip is over here in the bottom. So we designed this board to have two audio signals input to the amplifier. We can either have an FM radio audio signal coming in, and the radio circuit is on the top right, or we can have a direct audio input from a 3.5 millimeter jack from here. The two audios can be switched, and the user can choose either to listen to the radio or from a direct input through the switch over here. Then the audio is propagating to our audio amplifier, and then through a filter and directly to an 8 ohm speaker. The radio can be also controlled through two knobs over here, which one is seeking channel up and the other one seeking channel down. We have a volume control and LCD which shows the channel and the volume. The board is powered through 5-volt Arduino board in the bottom, which another purpose of the Arduino board is to control the FM radio receiver through I2C protocol. Now we're going to show you a functional demonstration of our project. So in the first demonstration, we will show you an input audio signal directly from an FM radio. I'm going to choose in the switch audio input from the FM radio. In the LCD we can see the channel and the volume. I can adjust the volume and I can sync for channels. Now I'm syncing down. For the second part, I will show you the demonstration with direct audio input from my phone. So I will switch this audio to the audio jack, and I can input the audio. I have to switch this one. And for the direct audio, I can also adjust the gain of the signal, which is basically the volume. Now I'm going to explain about the block diagram of the Class D amplifier that we designed. The signal is injected from the left and goes straight to the integrator. The purpose of the integrator is to compensate over voltage variations from the output stage of the amplifier, and is connected with this feedback that we can see through a resistor RF. The signal is then propagated to the comparator and is being compared with an internal triangle wave generator that we have in our chip. The triangle wave generator is generating a 500 kilohertz triangle wave, and through the comparator we are achieving a PWM signal. The PWM signal is then injected to the non-overlap generator, which generates a delay between two signals that are going to the NMOS and the PMOS of the driver stage. The purpose of the non-overlap generator is to make sure that we don't have inrush current, or in other words, making sure that the NMOS and the PMOS are not in on position at the same time. All the parts that are in the green dotted line are the components that were designed in the chip. The output stage of the amplifier is a low-pass filter, and the purpose of the low-pass filter is to reconstruct the original audio signal.
Now I'm going to show you the measurement of one of our internal signals, the triangle wave generator. To do that, we first enable the triangle wave observation pin from the PCB board. As you can see from this oscilloscope, so this triangle wave match very well with our simulation. In this experiment, we are generating a 1 kilohertz sine signal from this signal generator into the input of this amplifier chip, and in the meanwhile, we are measuring the output from our amplifier chip. As you can see from this oscilloscope, the blue curve represents the input sine wave, and the yellow curve represents the output sine wave. As we can see, we can get a clean output curve with a gain of 4, which is approximately the value that we designed.
We would like to acknowledge Professor King and the TAs of the class for the guidance during the semester, as well as we also would like to say thank you to Moses for giving us the opportunity to tape out our designs. Thank you very much.
Thank you.